Hello, gentlemen. Welcome to our video for the Chapter 19 practice. This is a supplemental video. It is not required for note taking. But here we go. Number 43 in your problem set says predict the sign of the entropy change of the system for each of the following reactions. So what this question is asking you to do is look at the degree of freedom of motion that is present within a problem from reactants to products. Meaning, if we look at A here, A has a gas. So we have gas N2 plus a gas H2 going to a gas NH3. I'm saying gas because gas is important. Gas is a state of matter that has the most freedom of motion. So those are going to be really important in terms of entropy because entropy is a measure of disorder, a measure of randomness. What's more random than a gas? In terms of states of matter, not much. So here in particular, we have 1 mole of N2, 3 moles of H2, and 2 moles of NH3. On the left side, we have a total of 4 moles of gas, and then we're going to 2 moles of gas. So you got to think, is there more disorder before or after the reaction? Well, there's more disorder before because there's more gas on the left side than the reactant side. Since there's more gas there, delta S actually decreases. You become less entropic, we say. Things have become more ordered, which means less entropy. So B, we go from a solid to a solid and a gas. Hey, well, we had a solid before. There's not much motion there at all. There's just vibrational motion in that solid. But then if we go to something that's a gas, well, ultimately in this reaction, we've increased the entropy because we created a gas from a solid. Even though there is another solid here with this calcium oxide, it being joined by this carbon dioxide just makes the entire product more entropic. All right, next one, we have 3 moles of this gas going to 1 mole of this gas. Now I know C6H6 is heavier, meaning it has a greater molar mass. So that does matter, right? The larger the molar mass, the more entropy you have. However, if we're comparing 3 moles of gas to 1 mole of gas, we're talking about 3 times Avogadro's number, right? So it's a lot of molecules different. So this one overall, delta S will decrease. We've decreased our number of freedom of motion. In D, we have aluminum oxide, solid, plus 3 moles of H2, which is the gas, going to 2 moles of a solid and 3 moles of a gas. Okay, so this one is a little tougher. We have the major particle we're looking at, gas, gas, right? We have 3 moles here and 3 moles there. Now you may be tempted to think, oh, well, we have 2 moles of solid here and 1 mole of solid there. So wouldn't, 2 moles of a solid be less entropic? Actually, in this case, the solids don't matter as much. And usually, actually in this case, they usually never matter as much. If you're comparing solid to solid, molar mass could take hold some weight there. But really, if we have gases present, focus on the gases. Right here, we have 3 moles of each, so the number of particles is the same. So freedom of motion of particles, the number of particles that are free are the same. However, the nature of the particles are not. H2O, just having larger molar mass, meaning more areas of rotation. You can rotate around this bond. You can rotate around this bond. A lot more vibration can happen because I have more particles here versus H2. So they're going to be pretty close. Entropy doesn't change very much here. But entropy does increase very slightly. due to water just being a more complex molecule, larger molar mass, more areas of motion. All right, 53. Using S naught values from Appendix C, calculate delta S naught values for the following reactions. In each case, account for the sign of delta S. I'm just going to do A. We've done this before. When looking at these not questions, meaning at standard states, we can easily use the summation equation. So we look in the back of the book in Appendix C. I've taken the liberty of already getting the values here. And we put them in. It's, hopefully easy peasy lemon squeezy here. For this particular problem, not this particular problem, all problems, we do product minus reactant. So my product is the 229.5 joules per Kelvin. I think technically in the back of the book it should be moles, joules per mole Kelvin. And we're multiplying times this here. This is your coefficient. The m and the n are your coefficient. My coefficient just happens to be the easiest one. It's 1 here. So I'll do that in the beginning. 1 mole, which is my coefficient, times my entropy here for my product. That's this. All done. If I had more than one product, I would add it to the other one, but I don't. Minus my reactants. So here I have 1 mole of each, so 1 mole of my first product times 219.4 joules per mole Kelvin. And moles cancel out. Moles cancel out. Plus my other reactant, which is 1 mole times negative 130.58 joules per mole Kelvin. Moles cancel out. So you would take the time to simplify this. I usually take the approach of doing this first and then use my scientific calculator to obviously put that number in again and then do that part second, but either way you want to do it, that's perfectly fine. So delta S here for A is that. Now the last part of the question says, in each count, account for the case of delta S. Account for the sign of delta S. Well, delta S is negative. Why? Well, we just had the last problem. There are fewer moles of gas in the product. So overall, we've become less entropic. It's gone down. 59. Using data in Appendix C, calculate delta H, delta S, and delta G at 298 Kelvin for each of the following reactions. In each case, show that delta G equals delta H minus T delta S. So I'm only going to do A here. These problems are kind of long, so I think that's why I only told you to do A and B. So for A, you want to find delta H, delta S, and delta G all using the appendix. So using those summation equations. For example, here at H2 plus F2 going to 2HF. They're all gases. This should be a G, looks like an S. And in the back of the book, delta H is 0 for H2, it's 0 for F2, and it's 268.61 kilojoules per mole for HF. Using my summation equation that I have here, I start plugging in. So finding delta H of this reaction, products. This should be an easy one. I have 2 moles here, so it's 2 moles times negative 268.61 kilojoules per mole. Moles cancel. That's my product. Minus my reactants. Well, they're both 0. So you just multiply 268.61 times 2, and we get negative 537.22 kilojoules. So that's your delta H for this problem. Is that the end of the problem? No. You got to find delta S and delta G. So delta S here below, here are my values from Appendix C. A little more complicated. So now I use my summation equation. Well, it should say delta S of the products. Okay, so now I plug in my product here has coefficient of 2, so it's 2 moles times 173.51 joules per mole Kelvin minus my reactants at 1 mole of each, so 1 mole, 202, that should be a parentheses there, 202.7 plus my other reactant, 1 mole, 130.58 joules per mole Kelvin. And I simplify. We get 13.7. Okay, go look back for a moment. Says in each case, show that delta G equals delta H minus T delta S in our temperature. And that's up here. Delta S, 13.7. Same exact thing for delta G here. In the back of the book, we get 0, 0, and negative 270.7 from Appendix C. So my summation okay, now we do products minus reactants. We have 2 moles of my product times negative 270.70 kilojoules per mole minus my reactants, 0 plus 0. Delta G for this reaction is going to be negative 541.31 kilojoules. Okay, so now the last part of the question, if there's 298 Kelvin. So delta G is, for us, we just found it as this. So we want to show, looking at this equation, if that's true. So let's just plug in. I'll erase this up. We're looking to find delta G to see if it matches this one. Delta H was given to us as negative 537.22. My temperature, 298. Okay, so obviously here, this is in joules, this is in kilojoules. So let's convert this 0.0137 kilojoules per Kelvin. So just make sure you account for that. Not a big thing here. And then you simplify. Delta G equals negative 541.31. Actually, you have to go back here. Sorry, guys. This one here is not 541.31. I was looking at the wrong value on my paper here. This is 541.40 for your delta G found from the back of the book, the Appendix C version. If you use this equation, you get negative 541.31, and let's not trip on the units here. They are kilojoules. And as you can see, they're pretty darn close, so it justifies that you can use the equation or the back of the book, Appendix C. Okay, last one. So octane is a liquid hydrocarbon at room temperature that is the primary constituent of gasoline. A, write a balanced equation for the combustion of octane to form carbon dioxide and H2O. Without using thermochemical data, predict whether delta G for this reaction is more negative or less negative than delta H. Okay, so first part should be pretty easy peasy. It's combustion, so hopefully you recognize that you need O2. And this is a liquid. This is a gas. And we're going to be forming carbon dioxide, gas, and H2O, liquid. Okay, so simple enough, we balance it. I'm pretty confident you guys can balance an equation, so I'm honestly not going to do that for you here. But once you do so, this is one of those ones where things aren't quite even, so you have to multiply the whole thing by 2. So we get 2, 25, this is going to be 16, and H2O, 18. Okay, and that will be your balanced chemical equation. Now B says without using thermochemical data, meaning no calculations, just predict whether delta G for this reaction is more negative or less negative than delta H. Well, to do that, you want to look at how delta G and delta H are related. They're related through the equation here. Now, we know that we're at some, obviously, this is Kelvin here, so we're at some positive temperature. There are no negative temperatures on the Kelvin scale, and we'll always be using Kelvin in these problems. So we have, let's look here. We have a positive temperature. So I'll just do positive temperature. And delta S, well, is it positive or negative? We can look at the equation to figure that out. We have 16 moles of gas here, 25 moles of gas there. So the gas is going to be leading the way, as I said before. We look at the gas because that's going to trump all the liquids or solids in the problem. So if you have gas, look at those. So we went from 25 moles to 16 moles. That's a decrease in particles, which means an overall decrease in the movement of particles. So we get a negative delta S. And negative times a negative gives you overall, this thing is going to be positive. When I say overall, I'm talking about this part, this positive. So if this part is positive, we now have delta G equals delta H. It's positive, right? So it's plus whatever this is. Now this is a combustion reaction. We know combustion reactions are exothermic. So this has to be negative. So if we have a negative plus a positive value, Delta G here, you're supposed to pick up that this is a combustion reaction. It happens pretty darn easily. Gasoline and oxygen react pretty easily, pretty spontaneously. So this should be negative. Now to make delta G negative, this negative plus this positive, this has to be a pretty large negative to eclipse this positive, making the whole thing negative. Mathematically, we're talking. Like this negative here for delta H must be large enough to, when added to this positive here, making the whole thing negative. So by that very nature, delta H is going to be a larger negative than delta G. So delta H is more negative. Delta G is less negative. That's how you would figure it out mathematically. And then that would lead to obviously your conceptual points on spontaneity. This reaction is spontaneous, but there are more spontaneous reactions with bigger negative values for delta G. All right, gentlemen, take notes. Hopefully this is helpful. Peace.